So, let's start from the place we had left. Let's clear it up. So, guys, for the love, for the love of getting to the highest grade, at some points, higher the grade is, the higher our chances are to impress people, showing our result and getting attracted by the best levels, like the best businesses, the best companies. We want to impress them, not impress them. They want to get impressed. Or if we want to make better companies, we have to be good. We have to be. We have to have an. We have to know what we're doing to beat them. So if we want to get to that point, we have to be good at what we're doing. We have to know all the rules of doing it. We have to get to that point so we can say we are good at XYZ and we're the best in XYZ level. So we are the best companies. How to say that? It's pretty simple, easy and simple. The things I was at. So three laws I was talking about. One is Newtonian's law. One is if an object is in position, it's gonna stay in its position unless a force is put onto it from outside. So if an object is still, it's going to stay still. If an object is moving, it's gonna keep moving, and motion is relatable. From here we can see that okay, I am still, but in terms of the earth is orbiting around the sun. Say that is sun. The earth is orbiting around the sun. Alright. Yeah, the law is like that. It does rotate like that. In that sense, I'm not still, or even the earth is rotating on its own axis. Counterclockwise all the time. That's why it's 23 hours 56 minutes or 58 minutes. 56 minutes, I guess. 58 minutes or something, or a few seconds. 56. So it's not exactly 24 hours. That's why we have a leap year after. It's a different thing. So that's why I can say that I'm not still, but see, I'm still. So it's related to the phone. The tablet is quite still, but and the person journeying from jet would tell we're not. It's all related. So there's quite much of motion. See, that easy. Nothing very hard. Another interesting part, say our say Golden Gate Bridge. Suspension, yeah. Pretty important. Sometimes we see bridges. Two wires are connecting two poles to foundation of the bridge. Very important foundation. It's kind of like the bone, the backbone of it. So which way is traveling? Is traveling as the way the where was set is kind of like a parabola. It's different topics. Math is fun. At the same time, there are few shapes we can use. Ellipse, parabolas, quite fun. It's part of physics as well, just for information. Parabolas are out there, and the other topics are out there as well, like different shapes. And there's another shape which goes with square. Parabola goes with double the amount traveled through x-axis and y-axis. But if it's square, then it's hyperbola. Alright, hyperbola is important. Say we're seeing some shape like this. It's kind of like a hyperbolic shape. So that's a little bit of math came up in the middle of. See, that's it's a higher level. That's the higher grade. This is the higher company level. So where were we? We were at motion. For us, whatever motion is quite relatable. It does vary. Motion does vary a lot. Let's stay on Earth. So later on, when you get to know about things, when you get to know about laws, I probably already do. Laws are two types. One is Newtonian, which is applicable only on planet Earth. But outside of planet Earth, when you go, Newtonian's laws are not pretty much applicable anymore, because there is a guy called let's see, I give an equation, try to remember the equation. Is a famous 1 equals mc square. Here it's a famous thing. Energy equals mass times the speed of light squared. So everything is very valuable. See, we might think that okay, we are not valuable, but we are that much. We do have that much energy. Our mass times the speed of light squared, sort of energy we are having. So when an object is traveling near the speed of light, when they have velocity like light, everything changes. And if we can get to that point, our science would get to another level, because we can travel much farther distance. Right now, we do not have that much velocity. We do not have anything, or we had encountered with anything with that much velocity. But when it happens, if we can shoot something at the speed of light, the first law says that the velocity is gonna stay the same. So if something's static, it's gonna stay static. But if something's moving, it's gonna keep moving. So if we can just shoot something at the speed of light, there's another thing, escape. So we have to go beyond the gravitational force and shoot things. If we can do that, and whatever velocity we get when escaping the gravitational force, it's gonna remain the same. So if we can get the speed of light once, we can keep that and travel to wherever we want, basically, because there's no stopping, no force is stopping us. So in that case, the energy is massive, because it's multiplied and squared, which is a huge number, speed of light. So everything has got that much energy. So Einstein did change a lot. So the guy who came up after Newton, so the Newton is only for the Earth. It's very old stuffs, but the new stuffs is applicable. That's why things are related. Things are pretty related. Say the speed, time. So three things that are pretty. So this is part of modern physics, right? Pretty easy, simple, basic, and yet pretty satisfying to learn. See, there are lots of topics to learn and study when we are young, but nothing as interesting as physics. That's why I feel interested to talk about physics. I could talk about lots of topics. I could go to let's go to that topics some other time. I could talk about lots of topics, but physics is something that's gonna create interest among the people who wants to learn. It's for everyone. So in modern physics, say we all know what Mr. Einstein did. Einstein got Nobel Prize for inventing something. So there are two theories. One theory is theory of relativity. He did not get Nobel Prize for that, guys. Just so you know, relativity. It is one of the modern wonders of the last century. I mean, which is the previous century, 1 century ago, but it used to be a very big thing. That's why this is called one of the best inventions in the last century, the previous century. So in the past century, the theory of relativity was a big deal. But he didn't get Nobel Prize for theory of relativity. He got a general relativity, which was in 1905, the theory of relativity 1915. So there's two things in two different time. He got the special theory of relativity, and there's some theory of special modification of the particles. So two things, but both were important. Theory of relativity was super damn important. He got for general theory of, one is special theory of relativity, one is general theory of relativity. So he got Nobel for the general one. We might think, okay, so the special one is special, so he should get some prize for the special one. No, he did get prize for the general one, not the special one. For some reason, quite interesting. But the theory of relativity changed a lot of things. He put when we travel the speed of light. I mean, we still do not. We wish we would. Very soon, some technology should come up. People should brainstorm and find ideas and brainstorm and get new technology, get new invention, get new modern science to get the modern technology go that far to reach the velocity of light, so we can use the theory of relativity. What happens? Three things. Time changes. Twin pairs, all heard of it. All saw the movie. We all saw movies, right? Interstellar, yeah. Everyone saw it. Pretty chill. Time relativity. What happens? If by chance not everyone saw it, time does vary in space. All right. So when you go to space, and even we are traveling at a much higher speed than we normally stay in here. So if one person is on Earth and another person is traveling at a very high speed, say 80% of the speed of light. I mean, 80% pretty much. We still don't have it. We wish we had. We wish we had the speed of light or higher. The higher speed, the better. The more distance we can cover. What happens? Time goes differently for the guys who are inside the spaceship. So, quite much time is relative. Two other things that's relative. Mass. When something's traveling at that speed, mass is different. All right. Interesting part. The things light that comes to Earth. Some people say lights got two particles. One is wave particle. Everyone knows it. Not pretty much yet effectively said, because we say, okay, light, say a torch. The light's coming straight. The light's coming right towards it. The light has some sort of like, the characteristics of light. It shows some wave motion. It has some characteristics of waves. So light particles do travel as a wave and also as packets, say photons. All right, we're not talking about photons of. We can talk about a lot, not in physics, but say photons, packets, quantas. So lights do travel as packets and also as wave. So pretty easy. So light has got two particles. In that term, what happens pretty good for light. Some people might say light has got mass, which is, people would be like, what the heck? Light cannot have it. Light's got nothing. Okay, it's got nothing, but some theories say quantum physics. We go. Lots of things happen in quantum physics because quantum physics do study about tiniest particles. 3D structure, tiniest particles. And when the tiniest particles move short distances, we have seen at some points some theories, some practicals, some experiments have shown that light did travel from one place to another without any time being spent for traveling. Quite fun. So what might have happened? It had gone through a tunnel of quantum. So quantum tunnel, very interesting topic. So quantum tunnel, say time is relative, mass is relative. Some other stuff are, say another stuff is. I'm coming to the other topic. So when something goes through the quantum tunnel, it doesn't really have to think about time because the time works differently in that quantum tunnel. Alright, it's like another universe, like a parallel universe, something like that. It does have connection. That's how the time does connect. We might have thought, okay, no time had passed, but the light particle had moved from here to here. Quite impossible, but in that tunnel, the time had been different. Quite interesting. So for us, a normal spectator, there was no time in the middle. That's why quantum physics, quantum mechanics, and quantum studies super interesting. We should put ourselves into it. Super interesting, super satisfying at the same time. Let's come back to our topic. So light has got different materials, particles. We have to think. We just shouldn't limit ourselves thinking that okay, we know the basic stuffs. That's okay enough. No, there are lots of experiments going on every single day. So we have to look after, say the movie, some Marvel movies, Iron Man, or say Avengers Endgame. We have seen quantum tunnel to another level. That's quite much a movie. But see, the fantasy that was shown in there is not pretty much a fantasy. Say, people say movies, anything can happen, but lots of things that happen in real life that had less sense to us unless we discovered that everything proves it. Say, who could say time is relative? No one could really say that, but no one really travels at the speed of light at the same time, right? How many of us has traveled in a spaceship, say in a rocket, or in a spaceship? Say twin paradox, that's another topic. It really simplifies it. Time is relative at the same time. So with the modern structures of lots of experiments, we all know time is relative. We all are not very much aware about these two. Pretty important. All the university guys are aware, and people who are studying are aware from long time. But it's for everyone. Say mass is relative. You can say how. Time does decrease in space. That's why someone who traveled from Earth and came back to Earth is much younger than his twin. He's much younger than the age he was supposed to be if he were on Earth. That's how time does decrease in space. Time goes slowly. That's why we count less amount of time, so it decreases. Mass decreases significant amount. So, say, on Earth, we are, say, X kilograms or X pounds. On space, we also might be 2x pounds. So our mass would be double. So normally in different places, gravitational constant on Earth is 9.8. Gravitational acceleration. That's where the weight comes up. That's